Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. We're in chapter 3, which is vector calculus. Today we're doing section 3.7, which is surface integrals, and this lecture specifically is going to be the definition of a surface integral of a function of 3 variables and examples. Let's do that. Alright, so for a surface integral of a function of 3 variables, what we're going to do is, first of all, we have a function f of x, y, z, which is of 3 variables, and we're going to have a surface with a parameterization, r of uv, over a domain D. We, starting for simplicity, use argue just as we did before over a rectangle, but you can be proved that it can be done over a general region in the UV plane. But we divide that rectangle into subrectangles, Rij. Those have areas delta U, delta V, and we saw that Sij is going to have area delta Sij, which is approximately equal to delta Tij, which is the tangent parallelogram. That tangent parallelogram has this area formula, the norm of Ru cross Rv, delta U, delta V. And therefore, the surface integral of a function of 3 variables over a surface S is given as the double integral over the surface S of f of x, y, z ds, which is defined as the limit of this double sum by picking sample point in the rectangle and computing f at pij star delta sij. To compute this, let's put the formula for delta sij as this area of the tangent parallelogram in there and give a computable formula for the surface integral. Alright, once again, noticing that the delta sij is approximately equal to the tangent parallelogram, which has this formula. We get that the differential ds is actually the norm of Ru cross Rv, du dv, and the computable formula for surface integral is the surface integral of f of x, y, z over S is equal to the double integral over the region D of f of r of uv, the norm of Ru cross Rv, times dA. In general, for rectangle, it doesn't matter whether I put du dv or dv du, but for a more general region, we'll just put dA, and then you'll have to set up your bounds and figure this out. Let's do an example of that. Alright, example, compute the surface integral of x squared over surface S, where S is the unit sphere, x squared plus y squared plus z squared equals 1. First of all, we get a parameterization of our surface S. We're going to use spherical coordinates where rho is 1. That's going to give me x is sine phi cos theta, y is sine phi sine theta, and z is cos phi. That means that our vector r, not uv, phi theta is going to equal sine phi cos theta sine phi sine theta times cos phi. I'll compute them, but I'll skip the steps of this. Is essentially looking at the Jacobian of transformation of spherical coordinates, but I'll quickly go over it in this form. That says that r of phi is going to give me cos phi cos theta cos phi sine theta negative sine phi, and r theta is going to give me negative sine phi sine theta sine phi cos theta and 0. Then I'm going to compute their cross product. It turns out that r phi cross r theta is going to equal 1 squared sine squared phi. If you can compute that. We've done this before, essentially in a different version in spherical coordinates, and that says that the norm of r phi cross r theta is going to be the square root of sine squared phi, which is going to be sine phi. What do we do with that? X also, remember, is going to be sine phi cos theta. That says that, and what are we doing? When we look at this, we have that 0 is less than or equal to phi is less than or equal to pi, and 0 is less than or equal to theta is less than or equal to 2 pi. That gives me the surface integral of x squared ds is equal to the double integral over the region d of the norm of r phi cross r theta d phi d theta, which is equal to the integral from 0 to 2 pi, the integral from 0 to pi of sine phi, oh, I forgot my function in there, f of r of phi theta times the norm of r phi cross r theta dA, which is equal to sine squared phi cos squared theta times sine phi d theta. I can separate this. This is going to equal the integral from 0 to 2 pi of cos squared theta d theta times the integral from 0 to pi of sine cubed phi d phi. Let's move that up and compute those two integrals. I have that the surface integral of x squared over the unit sphere is going to be the double integral over the region d of f of r of phi theta times the norm of r phi cross r theta dA. We computed that and simplified to this. I split the integral. Now I have to use two formulas. This is going to equal, first of all, the integral from 0 to 2 pi of 1/2 1 minus or plus cos 2 theta d theta times the integral from 0 to pi of sine phi. I'm splitting it, the cube, into 1 and then sine squared. Sine squared is 1 minus cos squared d phi. So I'm using a bunch of trigonometric identities. These are trigonometric integrals, and we have, this is case 4, which says we only have even powers of sine and cosine, and this is case 1 where I have an even power of sine and no coses, or an even power of cos. What does that give me? That gives me, this is equal to 1/2 theta plus 1/2 sine 2 theta evaluated from 0 to 2 pi times, using substitution, I'm going to use w equals cos phi. Then when I put that in there and make the substitution, I'm cleverly going to get cos phi plus 1/3 cos phi evaluated from 0 to pi. That should be cubed. When I compute that, this is going to be 0 from 0 to 2 pi. That is going to give me pi, 2's will cancel, times, then what am I going to get here? I'm going to get negative cos of negative, which is 1 plus 1/3 negative 1, and then we're going to get minus, which is now going to be minus negative 1 plus 1/3. That gives me pi times 1 minus 1/3 plus 1 minus 1/3, which is pi times 2 minus 2/3, which is 6 over minus 2, so this is 4 pi over 3. Please subscribe right here, hit the notification bell. I'll see you next time.